This is the first of several videos that's going to cover Carey's Chapter 8, titled Normal Linear Regression, that I typically refer to as simple linear regression. The idea of normal linear regression is that the observations are going to be deemed to have arisen from a normal population. So, if we think about simple linear regression, it is in fact quite simple. We've got a single predictor variable, that's the independent variable. So there's our independent variable year, and our dependent variable, the thing that we're trying to predict, is pop size, which is the population size, some sort of a bird species, as it varies with increasing years, as it varies with time. So if we plot pop size against time that we represent as years, what we get is this plot like this. And some of the things we might be interested in would be the slope of this line, the intercept here. And so since this is normal linear regression, we're going to assume that each one of these observations arises from some normal distribution. It's going to have a standard deviation sigma. We might also be interested in estimating that. So our model statement is going to be fairly straightforward. We'll begin, as always, at the bottom with a likelihood function. And what we're going to say is that these 16 values are population size. So here we've got our years. Here I've got our population size. They're implicitly indexed by I, which corresponds perfectly to year. That these 16 values of population size are going to arise from a normal distribution. They're going to arise from a normal distribution which has a mean, mu I, and again the mean is going to vary with I, it's going to vary with year, and some sort of a precision that we're going to represent as tau. Now, in terms of our mu I, we're going to model it like this. That's what mu I is equal to. So mu I is going to be equal to alpha, the intercept, plus beta, the slope, multiplied by year I. So that's going to be a likelihood function right there. So it's really pretty simple. What we're going to be interested in doing is, as I said, evaluating these parameters alpha and beta are going to be a primary concern. So if this is our likelihood function, what's left is to specify the priors, and these are all our priors. So if we think about converting all this stuff here into the model statement, here's our model statement. Quotation mark, keyword model, parenthesis, parenthesis, quotation mark. We'll begin with the likelihood function, open and close brace. These two lines here, we decided that this is our likelihood function. This likelihood function here is represented in code quite clearly here. So we're saying the population size is going to arise from this normal distribution with mean mu I and precision tau, and mu I is going to be obtained by this formula here. And so then what we need to do is get our priors. So what's going to happen is the prior for alpha is going to be flat, prior for beta is going to be flat, and the prior for our precision tau is going to arise from this two-stage process, where first we say that sigma, the standard deviation, comes from a uniform distribution, and then tau is just the reciprocal of sigma squared. So our model is really quite simple. There's one little wrinkle at the end, and that's this thing here that says P decline equals 1 minus step beta. What's that all about? What we're trying to do is determine the probability of getting a positive slope versus a negative slope. And the function we're going to use is this step function. So there's the step function. So how does the step function work? Well, it's going to operate on beta. It's going to operate on beta, which is our slope. And what's going to happen is the way JAGS works is that we're going to do 9,000 iterations of this thing because we're going to have 3 chains and 3,000 iterations at each. And each one of those 9,000 iterations, this thing here is going to be implemented. But again, what does this step function do when it operates on beta? Well, that's shown here is that if beta is greater than or equal to 0, the value of step, beta, is going to be equal to 1. In contrast, if that's not true, if beta is less than 0, then what's going to happen is the value of step beta is going to be equal to 0. So let's think about what's going to happen is if we've got a negative slope, then step beta is going to be 0, and 1 minus step beta is going to be 1. On the other hand, if we've got a positive slope, then step beta is going to be 1, and 1 minus step beta is going to be 0. So with all of that, we can look at our results. What we're probably going to be most concerned with is beta. And you can see beta is the slope. And if you look at the median, the mean, and the mode, they're pretty consistent. And you see there's the 95% credible interval from there to there. And if we look at the plot, that seems to be consistent in the sense that, okay, these are our means, medians, and modes, minus 1.57. That seems about right. 95% credible level, minus 2.2, minus 0.97, minus 2.2 would be right there, minus 0.97 just be about there. So that all makes sense. And how about our P decline? Though the answer for P decline seems kind of silly or kind of strange in that when you look at the output, it's got this $sign and it's got this warning about the chains being non-stochastic. What's happening here? What's happening here is you think about what this P decline is doing. It's the probability of getting a negative slope. In other words, it's the probability, it's a reflection of the slope. And so if you think about the posterior distribution, so what we're looking at here is the posterior distribution of beta. That's our slope. And there is 0 right there. So when you look at it, it's almost certain. And that's not surprising, given the strength of this relationship. It's almost certain that in all those 9,000 iterations, the slope is going to be negative. And as a consequence of the slope being negative, given the way we calculate P decline, we're going to get essentially all 9,000 values are going to have a value of 1, which is why we get this warning.